Let's see, we'll unpause that. So the first thing I want to do is go back over the rectifier and the turn-ons and such, because I realized I was working on it at the end of the class and after you guys left, and I think it was a little dumb luck that Robert and I got close to the right answer, because at least in my case, I was plugging in degrees and not radians, and everything we do here it's with radians, circular frequencies like omega t. And also, I wanted to know exactly the peak to peak. I knew it was about 20. So now here's the output of the transformer, and I put cursors for the peak to peak, and you can see it's 21. And we got 16.6 milliseconds, which is giving us 60 hertz, just as we expect. So then I put it through the rectifier, and at first I was a little disappointed because I thought, and maybe it's not supposed to be twice. Oh yeah, of course it's twice the diode drop. That's another mistake we made, Robert. We used 0.6 instead of one. We should have used 1.2 because no, 0.6 will work. That's right. I gotta think that one through now. But anyways, you see the rectified signal. Notice the time marks now, how far away spaced they are, because now this negative lobe is here. And we've cut out the bottom half. Still have the same frequency, but now my peak to peak is 9.3. So with a 21 volt peak to peak, my amplitude is 0.05, is 10.5. And then if I subtract the 9.3 that I get with the rectified signal, I notice that it's 1.2, which is 2 times the 0.6. Now, is that right? Oh yeah, of course it is, because it would be on both sides, like, right, because if I folded down the, so I like that, 1.2. So we wanted to demonstrate that this was due to the turn-ons of the diodes, and so I went ahead and we measured. At first, Robert and I got about 800 microseconds, and then he refined it down to about 500. And part of the debate was, in the book, he shows the 0.6 in the middle of the turn-on curve. So I remind you that for a diode, if you have X and Y axes and the x-axis is voltage and this is current, when I'm at negative volt, so that means negatively biased, reverse direction, but it doesn't instantly just turn on when you cross 0. It has this turn on, and then the slope goes infinite. This is an infinite slope. Now in the book, he shows the 0.6 here in the middle of the turn on. But if that was true, then I would imagine that now I forward bias it even more until I get the infinite current, and which is limited by putting a resistor. I would think then the diode drop would be higher, right? Because I would see that forward biasing I need to get to the infinite current, which is basically above whatever voltage that is, and then the current will just be the voltage from the battery minus the diode drop divided by whatever resistance is in the line. So my feeling is that he's drawn that improperly, and and it's a simple question of wiring up the circuit again. I didn't ask you guys to do it, so you wouldn't have the data to study. So the point being is, where do I put these cursors? And you notice that with sine, this slope is kind of curved like this. And then it's going to cross the zero and start going like that. But you notice here that it's crossing, it's already changing its slope, but that's the turn on of the diode. That's why the slope changes there. So I would assert that the correct place to measure this time is when this thing hits zero, not in the middle of the curve. Because then we know that's the place where the diode is shutting off, and that's at, and so that would be lower than 0.6, wouldn't it? So that's interesting. I got to map the diode out. So it's probably a little less than 0.6. And that would account for what you'll see in a minute. Okay, well, I can refine this, but I've gotten to the point where I'm within plus or minus 10%, so I tend to want to just give up. So what we did is that we set up a trig equation, and we use cosine, but I want to explore the behavior about zero. And so the best function would have been then sine. And remember, so I have some amplitude times sine of omega t. And we've determined that the amplitude is going, instead of 10, is going to be 10.5. And also omega equals 2 pi f. So then this equals to 10.5 times sine of 2 pi, and we have a fixed frequency, and then we have time. And we want to know if I start at t equals 0, when does it equal to 0.6? So once again, I have my sine of 2 pi 60t equals 0.6 over 10.5. And so that means that 2 pi 60t equals sine to the negative 1. Oops, that's over here. 0.6 over 10.5. So t is got to then equal this expression. So I'm just going to be lazy. 2 pi 60. So when you plug that into your calculator, you have to make sure you've set your calculator into radians instead of degrees. And so let's see. Here we go. So now I'm in radians. So I have 0.6, enter, 10.5 divide. Then I have inverse sine. And then I'll enter that, and then I'll divide by 2. And then I will divide by pi. And then I will divide by 60. And I get 0.152 microseconds. Which is a little surprising to me because I did this out on, oh, I know what's wrong with my spreadsheet. Okay, I can tweak up my spreadsheet a little bit. All right. And then, so then I double that, and I get 0.304, which is 300 microseconds. So it's kind of close. I think maybe I've got to examine the diode behavior. This says 400 microseconds. And then I ran it through a spreadsheet, and I used 8. So I used 8 volts, remember? And wait a minute. Should it have been 8 or should it have been good question. Yeah, it should have been 10.5. And so let's see what it gets us. Let's change this to 10.5. I forget why I picked 8 now. 10.5. And now let's redo this. And yeah, things changed. And where does it become 0.6? Right where right where it said earlier at 1.5, 0.155 milliseconds. Okay. So that's consistent. It's a little different than what we see on the oscilloscope screen, but don't forget there's stray capacitances and things like that. I could refine that. But the point is that we've hit the ballpark there, and we basically are demonstrating that it's the turn on. Okay, so let's see. I'm going to stop